Hello everybody, getting ready to do lesson 3.6 of Pre-Calculus Math Today, part 2. If you need a classwork sheet, email me here. And let's get into our lesson today, part 2, 3.6 Nonlinear Models. And you have 0 points here, notebook taking. You got 48-point classwork sheet today. And we just go right into our first example here. Example 3, fitting a model to data. The table shows the yield in milligrams of a chemical reaction after X minutes. And so we have minutes here, then our yield. Use a graphing calculator to find a logarithmic model and a linear model for the data and identify the coefficient of the determination for each model. Determine which model fits the data better. So we have time here, then we have a yield. A yield of what? Well, we're not sure yet, but let's go. Begin by entering data into a graphing calculator, then use the regression feature of the graphing calculator utility to find logarithmic and linear models for the data. So knowing that, okay, moving into our next slide here is page 11. So here is our natural log model here, a plus b natural log x. This is our natural log model, and we come up with our r squared is our variable of determination here, 0.99, that's pretty good. And then here is our graph of that using our natural log model. So log model for data is here, 1.58 plus 8. 0.373, 1.538 plus 8.373 natural log x. So here's our b. And the linear model for the data is 2.29 plus 2.3 here. So it is ax plus b. So here's our ax plus b, 2.29x plus 2.3. And the graph of that is here. So it seems like here, what's our determination variable here is 0.90. And this over here is 0.99. So this is a way better match for that data. To determine which model fits data better, compare the coefficients of determination. So here again is our natural log model. The model whose coefficient of determination is closer to 1 is the model that fits the data. In this case, the better fitting model is the log model because we have a coefficient of determination is 0.99. So that's pretty good, pretty close. Okay, into our problem here, our guided practice. We have a word problem here. Populations in millions of the United States for the years 95 through 2008 are shown in the table where T represents the year. So here is our T here, but T equals 5 corresponding to 1995, which is here, T equals 5. A, use the regression feature of a graphing calculator to find a linear model for the data and to determine the coefficient of determination. Plot the model and data in the viewing window. So put your coefficient of the determination here and then graph this data using a linear model. 6 points for this page here. And then B, the B part of this, use the regression feature of your graphing calculator to find a power model. So going after a power model for the data and to identify the coefficient of determination, put that here. Plot the model and the data in the same viewing window. So this will be your power model here. So that's what you see on your classwork sheet. So this is C. We got a part C here. Use regression to form an exponential model. So linear, power, and exponential here. Put your coefficient of determination here as well for that data. And then we have a logarithmic model, part D. So we have a logarithmic model E. Which model is the best fit for the data? Explain. So that we got a 4-part word problem here worth 8 points here for this. And then F, use each model to predict populations of the United States for years 2009 through 2014. You got a table here. So to predict populations 2009 through 2014, 1, 2, 3, 4, 5, 6 would be cover that. So linear, power, exponential, and then log. So for that, and then this page here is worth 8 points here for this too. And then G and an H. Which model is the best choice for predicting? Were your choices of models the same for parts E and G? If not, explain why. And then this part here is 8 points for this page. Okay, going back to solve these now. Okay, so here is our data. And then here would be your P, would be what your linear model would be here. And then our coefficient determination would be 0.9987, that's pretty close. And then this would be your plot in your graph here for part A. Part B, using the power model for that. Once you crank that in and then crank through your power model, 0.98, that's pretty close. And then here is your power model function, and then that would be your graph using your power model there. And then for your exponential model, again cranking that through, and then you have a coefficient determination of 0.9972. That's pretty good as well. All these fit pretty well. And then that would be your graph there using your exponential model. And then using a logarithmic model, what you should have, your coefficient determination here is 0.98, not as good as the previous functions. This would be your function here actually. And then your graph here, this would be your graph here. It seems like it follows a curve here for sure, but down here, not very well. Up here, it seems like it starts to variate. And then which model is the best fit for the data? Explain. The linear model is the best fit, closest to 1. And then for your tables here, your tables here for 2009, 2014. Here's your table for your linear model, your power model, your exponential model, and then your logarithmic model. That should be on your table. Population in millions. And then you have your year, and then your population, year, population there. And then which model is the best choice to explain. So G and H answers will vary, so it's up to you between G and H for both of these. You can surmise that on your own for that. And that is your part 2 of 3.6, pre-calculus math. Email me here for questions or classwork sheets or solution PowerPoints. Thank you.